Alright, so let's take a look at the June 2012 Unit 5 paper. So we've got an immersion heater supplying some energy, and we've got some water flowing through it, because that's how an immersion heater works. Assuming all the energy is transferred, calculate the rise in temperature of the water as it flows through the heater. So we are supplying 8.5 times 10 to the 3 watts of power. So if we divide that by the mass of the water flowing through per second, and we also divide it by the specific heat capacity of the water, we'd essentially, we can check this with the units. So basically on the top line we've got joules per second, on the bottom line we have kilograms per second, and then joules per kilogram to Kelvin minus 1, so your joules cancel, the kilograms cancel, the seconds cancel, leaving you with just K on the top line, so you know that's the temperature. So if we put that in and we calculate the answer, that is going to be 17 Kelvin. Two significant figures there. Cool. The water suddenly stops flowing at the instant when its average temperature is 26 degrees. The mass of water trapped in the heater is 0.41 kilograms. Calculate the time taken for the water to reach 100 degrees if the immersion heater continues supplying energy at the same rate. So the total energy you would need to provide is going to be mc delta T. So that's going to be 0.41 times 42,400 times by 100 minus 26. So let's whack that in the old calculator. So we've got 100 minus 26 times 4,200 times 0.41 is 127,428. So time is energy divided by power. So that's the energy, so it's the 127,428 divided by 8,500, which is 14.99, yada yada yada. So it's effectively going to be 15 seconds for two significant figures. Alrighty. So we're now moving on to some radiation. So we've got a uranium-238 isotope, and it decays into 206 by means of alpha and beta minus. We've got 8 alpha decays, and we want to work out how many beta decays. So 8 times by 4, 2 is you're going to end up changing the nucleon number by 32, and we're going to end up changing the proton number minus 16. So we've got 2, 3, 8, 92 minus 32, 16 is going to give us overall 238 minus 32 gives us 206. And then 92 minus 16 gives us 76. And we want to get to 82. So beta minus decay increases the proton number without changing the nucleon number. So essentially we want to get to 206.82, which is 6 sets of them, so we're going to need 6 beta minus decays. Okay, what is meant by the binding energy of a nucleus? So you can define this in two ways. There's the energy to split a nucleus into its constituent parts, or the energy released when a nucleus is formed. I typically go with the splitting one, so the energy required to split a nucleus into its constituent protons and neutrons. Alright, let's move on. So we've got a binding energy per nucleon for some of the stable nuclides. Use figure 2 to estimate the binding energy in megaelectron volts of the 20682 nucleus. So 206 is going to be around here. So what's that? 78.7, I would guess, from looking at the graph. So 7.87 is the binding energy per nucleon times by the number of nucleons, which is 206. 7.87 times 206 gives us 1621.22. So that's what going to be 1.6 times 10 to the 3 mega electron volts there, because you've taken our binding energy per nucleon in mega electron volts. Okay, so let's move on to the next one. The half-life of uranium is this value, which is larger than all the other ones. A rock sample was originally contained this many atoms, and no atoms this. At any given time, most of the atoms are either those two with a negligible number of the other ones. Sketch on a graph to show how the number of 238 atoms, the number of 206 atoms varies over a period of time. So the initial one is going to start at the 3 times 10 to the 22 value and essentially exponentially decay over time. If we've been given a half-life for this, 4.5 times 10 to the 9, so it should halve by 4.5, so that's going to be going through there, and it should halve again after 9 years, so it should be now at 0.75, so something like that, and we know it starts off somewhere up here, so we're going to get it to go as a rough sketch, something like that. So this one is the uranium 238 graph. Okay, and so the other one should be the opposite of that graph, because we're starting off with none, but then we're going to increase to have some, so it's going to look something similar, because it's going to go through this point here as well, because it said if they all decay into each other, and then we should end up with I don't know, something a bit like this. So it's the essentially the opposite. So when that one tails down, that one is going up, and it should look something like this. So it should be the inverse graph, but we shouldn't be gaining any atoms. So they, at all points, they should add together to give the total number of atoms. Okay, at a certain time after its formation, a sample contained twice as many 238 atoms as Pb. So that means that we can get an algebraic expression. So we know that U plus Pb is equal to 3 times 10 to the 22, because that's the total number of atoms. And we know that we also know that U is equal to 2 Pb, or Pb is U over 2. So we know that 3 U over 2 is 3 times 10 to the 22. Let's cancel those. So we therefore know that the number of uranium atoms is 2 times 10 to the 22 atoms there. And you can kind of see that just from looking at the numbers actually, but it asks to show you it to show that, so that's how you show that. And then calculate the time in years. So we know that it's governed by this equation like this, and so we know that we've got 2 times 10 to the 22 there is equal to 3 times 10 to the 22 e to the minus lambda t. So we cancel those two. So we know that minus the decay constant times time is log 2 over 3 like this. So we need to work out what the decay constant is. So to get the decay constant, we need to do log 2 over the half-life, which was 4.5 times 10 to the 9, which is, let's calculate that, log 2 divided by 4.5 times 10 to the power of 9, which is 1.54 times 10 to the minus 10, which means that time is going to be log 2 divided by 3 divided by the answer we've calculated times minus 1, which is, so when we calculate that, so it's 2.6 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 years, because we used the half-life in years, so this is going to give you an answer in years there. So to get the units, this 4.5 times 10 to the 9 was in years, so it gives you your decay constant in probability per year, so then you end up with a t in years once you rearrange it. Okay. In a radioactivity experiment, background radiation is taken into account when using corrected count rate. So one source of background radiation is the rocks on which the laboratory is built. Give two other sources of radiation. So the largest source on Earth is from radon gas, so that's almost certainly going to be contributing to it. So we might have some nuclear waste. We might also have some cosmic background going on there. Maybe some like carbon-14 from nature, a radioactive leak possibly, even from the sun possibly we could get some. Lots of places we can get that from. So we've got a detector with a certain area, and it's a certain distance from the source, and we've got a corrected count rate we've measured. So we're assuming it is emitted in all directions, so that the ratio photons in the detector, photons in the source, is about 4 times 10 to the minus 3. So the key thing is, I think a diagram helps with this one. So the photons are spread over an area. It's not a particularly great diagram, but it's spread over a 3-dimensional sphere. But the detector only occupies a small area of the sphere over which it is scattered. So what we need to do is work out essentially the ratio between the area of the detector and the area of the sphere. So the cross-sectional area of the sphere, not cross-sectional area, sorry, the surface area is 2 pi r squared, which gives you the surface area of a hemisphere, so actually we need to times that by 2 to give you a sphere. So that's going to be 4 pi times by 0.18, which is the radius squared, which is 4 times by pi times by 0.18 squared, which is 0.407. So the total number of photons on the detector, so the ratio is going to be the ratio between detector and the surface area of the sphere. So we've got an area of the detector is 1.5 times 10 to the minus 3, divided by 0.407, so let's type that in, 1.5 times 10 to the power of minus 3, divided by answer 3.68 times 10 to the minus 3, which is approximately 4 times 10 to the minus 3. And it doesn't have a unit because it's just a ratio. Okay, so measured activity at detector is going to be the 0.62, which was the corrected count rate, and we're going to times that by 400 because that would tell you how many actual counts there are. And then what we're going to want to do is then work out the total activity. It's going to be that value, 0.62 times 400. So that would be the total detected, and we want to divide it by the 3.68 times 10 to the minus 3 to find out what the total number would be. So that's going to be 0.62 times 400 divided by the previous answer, which gives you 6.7315 times 10 to the 4. So we're going to give that as 6.7 times 10 to the 4 to two significant figures, and activity is in becquerels. Calculate the corrected count rate when the detector is moved 0.10 further from the source. So we're going to be using the inverse square law. So the initial activity over the final activity is an inverse square law, so it's going to be in proportion to the distances squared in this way. So you can see that as you get a bigger R2, essentially that ratio gets bigger, which is what you'd expect. So we want to calculate A2, so it's going to be the activity measured and then R2 squared. So it's 0.62, which was what was measured before. Then we've got 0.18 squared divided by 0.28 squared, which is the new distance. 0.62 times 0.18 squared divided by 0.28 squared, which is 0.256, which is approximately 0.26 counts per second. Okay, question 4, so moving on to some thermal physics. So we've got a pressure inside a tyre, we've got a volume, and we've got a temperature. So we want us to calculate the number of moles, so we're going to be using the ideal gas equation there. So we want N is going to be PV over RT. So let's put those values in. So PV is going to be 3.2 times 10 to the 5, minus 1.9 times 10 to the power of minus 3, divided by 8.31, which is R, divided by 285, and that's going to give you a value of 0.256, so it's approximately 0.26 moles. Okay, so after the bicycle has been ridden, the temperature has increased. Volume is unchanged, so calculate the new pressure. So if volume is constant, we know P1 over T1 is equal to P2 over T2. So P2 is going to be P1 T2 over T1. So the original pressure was what? 3.2 times 10 to the 5. minus by the new temperature divided by the old temperature. That's going to come out as 3.2 times 10 to the 5, 3.2 times 10 to the 5, minus 295 divided by 285 gives you 3.3 times 10 to the 5. Actually, it's going to be 3.31 because we're going to give it to 3 significant figures because that's 3, and that's 3. And then the 295 is 3, so we're going to give this 3 significant figures, so we'd give it 3.31 pascals there to the right number of significant figures. Okay, describe one way in which the motion of the molecules of air inside the bicycle tyre is similar, and one way in which it is different at the two different temperatures. So similar, so the motion of the molecules will still be random. So when you're modelling gases, we always assume their motion is random, so we'd expect that. So what would you expect to be different? So your temperatures increase, so the internal energies energy is increased. Which means I find that the mean square speed is increased when your temperature is increased. So that's what you'd expect to change. Move on. Okay, a nuclear radius question. So sketch on the graph to show how the radiance of a nucleus varies with its nucleon number. So we know it's this equation is to the power of a third, so we're going to go kind of like this, and your gradient's going to decrease as you increase nucleon number. The radius of a gold nucleus is this value. Show that the density of the nucleus is about 2.4 times 10 to the 17 kilograms per meter cubed. So first, the mass is going to be 197 times 1.66 times 10 to the minus 27, which let's calculate that now. So 197 times 1.66 times 10 to the minus 27, which is 3.27 times 10 to the minus 25. So to get the density, we need to do the mass over the volume, which is 3.27 times 10 to the minus 25. And we're modelling it as spherical, so we're going to do 4 over 3 pi times by 6.87 times 10 to the minus 15 cubed. So let's calculate. So divide by 4 divided by 3 divided by pi divided by 6.87 times 10 to the power of minus 15 power of 3, which is 2.407 times 10 to the minus, sorry, not minus, to the power of 17, which is roughly 2.4 times 10 to the 17 kilograms per meter cubed. Okay, using the data from part B1, calculate the radius of an aluminium 27 nucleus. So nuclear density is approximately constant. So we could get the volume by doing the mass divided by the density, so that's going to be 27 times 1.66 times 10 to the minus 27 divided by 2.4 times 10 to the minus, not minus, it was plus 17. So let's do that calculation. So 27 times 1.66 times 10 to the minus 27 divide that by the answer, it gives you a volume of 1.86 times 10 to the minus 43. So that's equal to 4 over 3 pi r cubed. So times it by 3, divided by 4, divided by pi, and then cube root it. Gives you a radius of 3.54 times 10 to the minus 15. All I think data was to 3 significant figures, so we can get this answer to 3 significant figures. So it's going to be 3.54 times 10 to the minus 15, using the fact that there's roughly constant nuclear density across all things. So I'm guessing, because we haven't had a longer answer question, we're about to see one. So let's see if I'm right. Oh, there we go. Nuclear radii have been investigated using alpha particles in Rutherford scattering and also electron diffraction. Compare these two methods. We don't need to talk about the apparatus, but we do need to talk about the principle on which the experiment is based, including equations, an explanation of what might limit accuracy, and a discussion of the advantages and disadvantages of each method. So let's first talk about alpha scattering. What are the key principles are there? So what's going on there is the kinetic energy of the alpha particle is transferred to electric potential energy there, so we can end up getting an approximation to the nucleus size, because we know if we know the initial kinetic energy, we can equate it to QQ 4 pi E0 R squared, and this R squared gives us an approximation for the nuclear radius. So that's often called the closest distance of approach. That's what it's known as. Whereas electron diffraction, so it's diffracted if wavelength is a similar order to the nucleus size. So we know that the de Broglie wavelength is going to be equal to the nuclear diameter. So it gives you a way of directly measuring the nuclear size there with electron diffraction. So those are the two key principles and the two key equations. So what we've done there is we've looked at this first part here. What might limit the accuracy of each method? So alpha also feels the strong force, but electrons do not. So this is one advantage electron diffraction has over the alpha scattering, because the strong force is a source of essentially a source of error in your measurements there. Okay, so that I would say is actually more looking at advantages and disadvantages in here. So we actually want to look at what limits the accuracy of each method. So if we're looking at alpha, so one possible cause of lack of accuracy is multiple scattering may occur. So all the observations of the alpha scattering experiment are based on the assumption that only single scattering occurs, so a source of error
or lack of accuracy would be that multiple scattering can occur. You also recoil velocity of nucleus is a source of error, because we're essentially modelling it as a collision between two particles. And the other option is the other problem is this method is an approximation. So it's not a direct calculation, it's an approximation. So that's always going to be a source of error. So turning us to the electron diffraction. One issue is it assumes uniform speed, so it assumes all the electrons are travelling at the same speed, which you almost certainly not going to be the case in this. Is very unlikely you're going to get one, but that's the only real assumption that you're making with the electron diffraction experiment. So if we go back, we've now really addressed the limitations of accuracy of each method. So I guess we've finished talking about the advantages and disadvantages. We've got the key one there, the advantage is to do with the strong nuclear interaction. That is the key advantage that electron diffraction has over alpha scattering, which is nice. But given this is a 6 mark, they're probably looking for 2 points to talk about on this one. So we need to think of another advantage or disadvantage of one of these methods. So what I think that's going to be is there's not really another one, but it's probably looking for a little bit more detail here. So it's probably looking for the fact that alpha are hadrons, but electrons are leptons. So that will be the extra detail it's looking at for a second mark there, actually identifying the types of particles, which explains why one can feel the strong and the other can't. So that's what's going to be looking for there.